Hello, everybody. My name is Rodrigo Moreno. Thank you for coming to this presentation. I will present our work that is called Characterization of the Mechanical Tissue Properties of the Brain in the Developing Brain with Magnetic Resonance Elastography. And this is a collaboration between me, that I'm with KTH, and Armita Golkar, with the Psychology Department at Stockholm University. Okay, we are interested in the developing brain and anxiety disorders. So during the adolescence, there's a dramatic development of the brain. And it has been shown that between childhood and adolescence, there is a peak of the onset of anxiety disorders. And so far, mechanical properties of the brain have not been assessed. And then we're interested in seeing if these changes could be related to the risk of developing anxiety disorders. So this is the main purpose of this project. Yes, and for that, this is our approach. So we are recruiting two groups of children, one that is from 9 to 11 years old, so more children, and the other is like more adolescents from 13 to 15 years old. And we are going to do two things. First is to acquire images, especially MR elastography, and brain connectivity. Brain connectivity is a method to assess changes in the connections between different regions of the brain, while MRE tells you the mechanical properties of the tissues. In addition to that, we are running some psychological tests, which are meant to get some risk predictors for developing anxiety. And our goal is to correlate these predictors from these questionnaires with the imaging data we are acquiring. So let's go for magnetic resonance elastography. As I said, this is a method to obtain mechanical properties of the brain through MRI. And this is how it works. So then it has three phases. The first phase is to excite the tissue, in this case, the brain. So then we have a pump, a pneumatic pump that is connected to a pillow that is put on the back of the head. And then it creates like some gentle up and down movements of the tissues. So these movements are acquired or are imaged with MRI. And with these images, after post-processing, then you get the stiffness, for example, of the tissues. KTH is proud of that is the only site in Sweden with this technology right now. Let's go more into the details of MRI. So first, we need hardware, of course. We need an MR scanner. And then we need a pneumatic pump that is synchronized with the MRI. And this is out of the room, the MRI room. So then this is connected with a hose to a pillow. That is exactly, this is the one that we are using here. And as I said, then it creates this gentle movements of the brain tissues. Yeah, with high frequencies of 50, 60 hertz. Once you have that, you need to image this displacement of the tissues. And for that, you use something that is called motion encoding gradients from MRI. And this is synchronized with the motion that you are inducing to the tissues. So then you can create these estimations of displacements with time. And this is how it works. So then this is what you acquire. And then after post-processing, this method is called inversion. So then we take these wave images that are this raw data that you acquire with the scanner, and then you estimate the mechanical properties of the brain. And this is how it looked like in our scanner. So then we have here just like an anatomic image, and this is what we acquired. So then you can see visually how the waves are propagating inside the brain in the X, Y, and Z direction, and this is time result. So this is the wave image, and then after inversion, then we can get the elastogram, which tells you how stiff or soft the tissue is in different parts of the brain. For some reasons, we are a bit delayed with the acquisition of the children's data, but we have other projects where we are also acquiring MRE. So I'm presenting here the results with for the project that we have with Parkinson's disease. So far we have scanned 9 patients and 9 controls, and we found even now that it's very clear. There is a very clear trend that tells you that the brain in the due to Parkinson's is softened. So then you can see here that the controls are always have higher stiffness, which means that are harder, while the patients have softer brains in different parts of the brain. We also checked correlations between MRE and diffusion-based measures, for example, fractional anisotropy or microfractional anisotropy. And as you can see, there is like some kind of correlation between MRE and diffusion. Also here in this other plot. So one hypothesis here is that maybe the fibrous volumes become it creates like a stiffer material. So that's why it's creates this correlation. But this is something that we are now looking more into the details to see if we can explain that correlation. Then we moved on to create a AI-based MRE inversion, because then there are methods that are available but are super time-consuming. So this is an example here. So this creating this elastography map, elastogram map takes a lot, like 1 day with nonlinear inversion. And then what we did here, just like a simple example, was to train a neural network to predict these values. So then you will have more or less the same results, but quicker. And actually we got 75% R-squared, which is not bad, but we were more interested in this correlation with diffusion. So then we added a lot of other modalities, for example, anatomical images, T1, direct inversion, that is like not as accurate as nonlinear inversion. And then FA, that is the fractional anisotropy that is related to diffusion, and then the raw data from MRE. And as the most interesting part was here, that we saw that there is like some correlation that around 40–50% R-squared, which means that still there is like some mild correlation between these two imaging modalities, which is something that we are right now looking more into the details. And then we moved on for creating new AI-based MRE inversion. So then there is this method from the literature. Basically, what they do is to create simulated stiffnesses, and then they use the equations of wave propagation to simulate the wave images, and then they have this as an input, and then this should be the output for training a neural network. So it kind of worked. It has an issue here, is that you need to create a lot of synthetic images then the estimations should be very accurate. And these two are very difficult to comply with. So and then another thing is that they didn't use real data. So we wanted to add this real data, and then we wanted to use physics-informed neural networks, which is a new method that you include the equations from physics, in this case, the wave propagation equations for in the loss functions, so then you can get better estimations of properties. But for that, we need good MRE simulators. So then we started with a very advanced one. So we asked a colleague from neuronic engineering department at KTH, and he created this very nice simulator that shows you how these waves are propagating in the brain. One problem of this method is that it's time consuming, because it's based on FEM. So we went down and said we wanted to have like the other extreme, to have something that should be maybe not too accurate, but quick, to generate millions of samples to train our network. And this is more or less what we found with Maria. So then it works. But we are not happy with the quality of the images. So right now we are implementing other methods that are like somewhat in the middle between FEM and this one. So hopefully we will have a lot of data to train on, and use our acquired data in our scanner to introduce also this real data in the loop for the MRE inversion. And this is it from us. So this, as I said, this is a collaboration with Armita. Christopher has been like the main driving force in this project. Jessica is helping us with the imaging. Joe created this FEM model. Maria worked with this simplified model for simulations, and for installing the MRE in our scanner has been very crucial. The collaboration with the people from Philips, and Fabian has been helping with the diffusion data. Thank you for listening.